this video I want to talk about how do we find the general form of the particular solution. The book calls the method that we're using to find the particular solution the method of superposition. There's other methods, but this is the method that I like the most, so this is the method that we're going to talk about here. And so what I want to do is for various differential equations and for various functions g of x, I want to figure out what's our guess for the particular solution. And so what I want to do is I want to kind of walk through, and first I'm going to give you a few kind of guiding principles, and then I just want to do a bunch of examples, and then from that, I don't want to write out, the process in general is a little bit tricky to write out, but understanding the process through examples I think is much easier. So I want to do the examples, and then we'll talk about the process at the end. So just kind of a few general guiding principles here. You should always find the complementary solution first. It turns out that there's information. When you find the complementary solution, what you're doing is you're solving the associated homogeneous equation, which has a characteristic equation, and you need to understand that characteristic equation to find the particular solution. So the point is that you need that information anyway, so always find the complementary solution first. Then you want to make a guess for the particular solution, and then once we have a guess for the particular solution, assuming that we're guessing the right general shape of our particular solution, then we can put them together and get the general solution. So that's really the thought process here. So find the complementary solution first, and then once we have the complementary solution, then you can guess the particular solution. So let's go ahead and let's look at a series of examples here. And I have a series of 15 or so 19 or so examples that I want to talk about. And so the first one that I want to talk about is let's find y sub p. And what I mean, I shouldn't actually say find y sub p. Find the general form of y sub p. I don't actually care what the constants a and b and c and stuff are. I just want to figure out what's the general shape of the particular solution. So let's find the general form of the particular solution so let's look at y double prime minus 2y prime equals 7 e to the 5x. And so what we have to do is we have to look at this equation, and we have to think about what's the complementary solution. And the complementary solution is we're going to have r squared minus 2r equals 0. So the complementary solution is going to be c1 e to the 2x plus c2 e to the 0x. So we have an e to the 2x and a e to the 0x, or constant, that's in the complementary solution. Those are the main terms there. And so e to the 5x is not, it does not appear in the complementary solution. To say that same sentence again, the e to the 5x is not in the complementary solution, notice that that means that 5 was not a root to the characteristic equation that we had to look at, r squared minus 2r equals 0. So 5 was not a root. So if 5 is not a root, that tells us that our particular solution is just going to be some constant times e to the 5x. Everything is totally fine. We don't have to do anything more. So we started with a constant times e to the 5x. Our guess is going to be that our particular solution will be a constant times e to the 5x. Let's look at y double prime minus 2y prime equals 7x e to the 5x. The process is going to be the same, and in fact, I haven't changed the left side, so the corresponding complementary solution is going to be the same as it was above. So we're going to have r squared. Let's just scroll so you can see it. So r squared minus 2r is 0. The complementary solution is still going to be c1 e to the 2x plus c2 e to the 0x. And we still don't have an e to the 5x in the complementary solution. In other words, 5 was not a root to the characteristic equation. So that tells us that our particular solution is just going to be, again, the way to think about this is that this is just a linear term times e to the 5x. So our guess for the particular solution is going to be a linear term times e to the 5x. And let's look at if we were to have y double prime minus 2y prime equals 8x cubed minus 4 e to the 5x. then again, 5's not a root to the characteristic equation of the associated homogeneous ODE, and therefore our particular solution is just going to be a general cubic, ax cubed plus bx squared plus cx plus d e to the 5x. Okay, so that would be our guess for the particular solution there. Okay. One more. So next, let's imagine that we have, let's look at y double prime minus 9y equals e to the 4x. And let's make it x squared, e to the 4x. Well, 4 is not a root to the characteristic equation of the associated homogeneous equation. In other words, pretend that this right side is a big 0. The solution to that equation, or the complementary solution, would be e to the 3x and e to the negative 3x. Those would be our linearly independent terms. So the complementary solution would be c1 e to the 3x plus c2 e to the negative 3x, meaning that 3 and negative 3 were the roots to that characteristic equation. 4 was not a root, so we didn't have to worry about it. So this would mean that we would have our particular solution would be a general linear term, or a general quadratic term, ax squared plus bx plus c, times e to the 4x. And then we could figure out the values of a, b, and c from there. Okay, so that's how that would work. Piggybacking off of that, if we were to have y double prime minus 9y equals, let's say, 4x plus 5, the right way to think about this 4x plus 5 is as a polynomial times an exponential. And the exponential that we're multiplying by is e to the 0x. 0 was not a root to the characteristic equation, so we don't have to do anything special. This tells us that everything's going to work the way that we expect it to. We're going to have a general linear term times our e to the 0x, or if you want, just ax plus b. So it turns out that would be the particular solution that we would look for, there. All right. Next, what I want to do is let's look at what happens if we have y double prime minus 9y equals 7 e to the 3x. What's going to happen in that case is, again, the left side is the same as the previous example. So we had e to the 3x and e to the negative 3x were our solutions to the associated homogeneous equation. Okay, so this means that we're going to have to mess with the particular solution just a little. So our particular solution normally would be a constant times e to the 3x. But because 3 is a root to the characteristic equation, I think this is actually worth writing. The characteristic equation is the equation r squared minus 9 equals 0. We have r minus 3 to the first times r plus 3 to the first equals 0. And, so if we look at this equation, the reason why I say that they're to the first is that the exponent is what's called the multiplicity. And what that means for us is that we only have to put an x to the first in front for a particular solution. So this would be ax e to the 3x. Okay, and that's how the particular solution would look there. If we were to have y double prime minus 9y equals, let's say, 5x squared e to the 3x, then something similar would happen to before. So again, this 3 here, we need to think about that e to the 3x is appearing in the complementary solution, and it does. It's a solution to the characteristic equation of multiplicity 1, like we said before. And so what's going to happen is we're going to have, so here we have a quadratic term times e to the 3x. So our particular solution is going to be this quadratic term, ax squared plus bx plus c, times e to the 3x, except that we have to multiply by another x, okay, because 3 is a solution of multiplicity 1. So we need an x to the 1 in front. Okay, so that's how that works out. So again, this is if this was some other constant like e to the 7x, then we wouldn't need this x term here. We would just have a general quadratic times e to the 7x, and that's fine. But since that's e to the 3x, and since 3 is a solution to the characteristic equation, we need an x in front, okay, because it's a solution of multiplicity 1. All right, so now let's ramp this up one step further. Let's look at y double prime minus 10y prime plus 25y equals e to the 4x. So nothing really to talk about here. 4 is not a root to the characteristic equation of the associated homogeneous equation, so all we're going to get for a particular solution is going to be a e to the 4x. So there's really that's all there is there. If we were to have y double prime minus 10y prime plus 25y equals, say, x cubed e to the 4x, then again, 4 is not a root to the characteristic equation, so our particular solution is going to be something like ax cubed plus bx squared plus cx plus d e to the 4x. That's it. Next, let's look at, let's say we have y double prime minus 10y prime plus 25y equals some constant times e to the 5x. So one of the things that I glossed over before that I should have spent some time on was thinking about the characteristic equation of the associated homogeneous equation. So we have r squared minus 10r plus 25 equals 0. And this means that this is going to be r minus 5 squared equals 0. And so our solution is going to be r equals 5, and it's a solution of multiplicity 2. So that's what that equation is going to look like. That's what our solution is going to look like. And so the way that this plays a role when we talk about the particular solution is that we're going to look at, we would normally have a constant times e to the 5x, like we did before. We had a constant times e to the 4x, and nothing wrong with that. The problem is that e to the 5x already appears in the complementary solution, and because it's a repeated root, so does x e to the 5x. That's already in the complementary solution. So what we need is an x squared, and there's two ways to think about that. The first way is that if you think about the complementary solution to any of these previous problems, let's just write it here. If you think about the complementary solution, that was going to be c1 e to the 5x plus c2 x e to the 5x. We talked about that reduction of order idea, about how you get the x e to the rx if you have a repeated root. And so our particular solution can't be x e to the 5x, just like it can't be e to the 5x, because those are both in the complementary solution, so we know that that can't work. So what we need is we need an x squared e to the 5x. So ax squared e to the 5x. So one way to think about it is that x squared is the smallest power of x that you can put in front so that it's not already in the complementary solution. I think a slightly better way to think about it is that it's x squared. It's x to the 2 power, because 5 is a solution of multiplicity 2. Okay, so we have ax squared e to the 5x. And then one step further from here, if we were to have y double prime minus 10y prime plus 25y equals, say, x cubed e to the 5x, and make it, but again, whatever constants don't matter, then we're going to go through the same sort of process. If we have a cubic term times e to the 5x, our particular solution is going to be some cubic term, ax cubed plus bx squared plus cx plus d times e to the 5x. But the problem is that these two terms, the x times e to the 5x and a constant times e to the 5x, are already in the complementary solution. So to make them not in the complementary solution already, we multiply by this extra x squared in front. And again, this is an x squared term because 5 is a root to the characteristic equation of multiplicity 2. Okay, so that x squared term there, again, this 2 and the multiplicity being the same is not a coincidence. That's why it's squared. Okay. So that's how we deal with polynomials and exponentials, and I think I've done all the examples that I need to there in terms of polynomials and exponentials. I guess actually one more that I should think about just so that we can have an example. I mean, I've basically already talked about this. But what would happen if you were to have, say, y double prime minus 4y prime equals e to the, so say 7 e to the 4x. So I'm going to have a few more than 19 examples now because I'm adding a few. But what if we were to have 7 e to the 4x? Well, we know that the complementary solution is going to be, let's see, c1 e to the 4x plus c2, because the characteristic equation is r squared minus 4r equals 0. So r is 4 or 0. So we get an e to the 4x and an e to the 0x. So that's fine. That tells us that our particular solution is going to be ax e to the 4x. Okay, so nothing really to worry about there. If we were to have y double prime minus 4y prime equals x squared plus 3x times e to the 4x, our particular solution would be a general quadratic term. So ax squared plus bx plus c, e to the 4x, and again, times an x in front, and that's because x is 4 is a root to the characteristic equation of multiplicity 1, so you get an x to the 1 in front. But just to be clear about how this works, if I were to have y double prime minus 4y prime equals, say, x squared plus 3x, but there's no e to the 4x after. So if we were to just have this, if we were to have x squared plus 3x, what would be our guess for the particular solution? So pause the video for just a second, think about it, and then come back. So if we think about this as e to the 0x, then the process is going to be exactly the same as it was above. We're going to have our particular solution is going to be a general quadratic equation, ax squared plus bx plus c, times e to the 0x times x. But e to the 0x is 1, so you don't have to write it. So whenever you have 0 as a solution to the characteristic equation, then you have to think about, if you have just a polynomial term here, this is like you have to worry about whether 0 is a root to the characteristic equation. In our case, it was a root of multiplicity 1, so we still need that power of x to the 1 in front, okay, just like before. This video is getting a little long, so I'm going to take a slight break for your sake, and then we'll come right back and talk about some more examples.